Hi there, my name is Brent, and today I'm going to be explaining the addition of IEEE 754 single precision floating point numbers. And in this presentation, I'm going to be showing you two examples, one of which is going to highlight the concept of the right shift, and the other example will show a step-by-step computation of the addition of these IEEE 754 single precision floating point numbers. Now in the first example, what we're given is two hexadecimal values that we're going to need to add, and the first step in doing so is taking the first value that we were given, which is C0D20004, and converting this into binary, which I have done so already right here. And then we're going to need to convert this into the IEEE 754 single precision floating point number. And in order to do this, we need to break it up into three different subgroups, which the first subgroup is going to be the sign, which is 1 bit, then the exponent, which is 8 bits, and then the significand or the mantissa, which is 23 bits long. And what this is going to correspond to is that you can plug these values into the expression shown down here, where for the sign bit we have -1 raised to, in this case, a 1, which means that our value is going to be negative. Then you're going to take the mantissa or the significand, which is 23 bits long, and you're going to add 1 to it and put it in this position right here. Then you're finally going to take this 8-bit exponent, which in this case is 129. You're going to subtract 127 from that, and you're going to get 2 to the 2. So the final value that you get is -1.1, then the rest of these zeros and ones, times 2 to the 2. And for the next value that we are given, we have 724,07020. In order to make the time quicker, I'm going to solve this out for you and put it right here, which in this case was 1.1 times 2 to the 101. And if you notice in comparing these two values, we have times 2 to the 2, which is going to be less than the times 2 to the 101. And so we shift the lowest number to the right in order to make the exponents equal. But if you look closely, you'll see that the 2 raised to the 2 is 99 orders of magnitude away from 2 to the 101. And because the mantissa is 23 bits, and we need to shift to the right greater than this 23 bits in order to make the exponents equal, then what this means is that our value times 2 to the 2 is going to end up being 0. Because, of course, when you shift to the right, you can imagine moving this decimal place over to the left, and 29, well, it'll be more than 23 times. And as you can see, when you shift these numbers to the right, it's going to eventually become 0. And therefore, that makes this problem pretty simple then, because all we really have is 0 times 2 to the 101, which of course is 0. Then we add that to the hexadecimal value 724,07020, which of course will give you just that value, 724,07020. Now for the next example, we're given two hexadecimal values, one of which you've seen already, which is the C0D20004. And for time's sake, I'm going to put that value for you right here. And in our next value, we have hexadecimal value 40DC0004, which I'm going to solve for you as well, and which comes out to 1.10111, then the rest of these numbers times 2 to the 2. Because these exponent values are the same, then we can go ahead and start adding. And when we add these two IEEE 754 single precision floating point numbers, it's just like adding regular binary numbers, where we have the 1.10111 times 2 to the 2, and we subtract 1.1 times 2 to the 2 from that, which using just standard addition concepts, we can see that subtracting 1 from 1 is going to give you 0, and of course 0 minus 0 is going to be 0 for the rest of these. And as you can see, for this example, we're going to need to borrow the 1. We're going to need to borrow the 1, which means we'll put a 0 in that place. And this expression is going to be 10 minus 1, or you can look at it as 2 minus 1, which is 1. Then the 0 minus 0, which is 0. Then we have the 1 minus 0 is 1, and then the rest of these will become 0. And so the final value that we get is going to be, after some shifting, you'll see 1.010 times 2 to the negative 2. And if we convert this into hexadecimal, the value that we are going to get is going to be the hexadecimal 3EA00000, and for our final answer. And that is how you add the IEEE 754 single precision floating point numbers. Thank you.